Hello. Hello.
Sir, sir.
Very good morning to all of you. I'm indeed very happy to welcome to the second day of the webinar, International Webinar on Materials for Energy, Environment, Healthcare Applications. Yesterday we had a session, the first day session, 3 lectures were there. On the second day, we have now Dr. Gautam Krishnan, who will be delivering his lecture in the morning, first lecture. Before he starts, let me introduce to the participants. We have with us Professor N.S. Nagarajan, former professor of chemistry at Gandhigram Institute, senior professor and motivator, an inspiring personality with us. And it is our duty to welcome him on behalf of everybody. And I request him to bless all of us through his benedictory address. So over to Professor Nagarajan. Nagarajan sir.
For your nice words. I am very happy to understand, to know that the Department of Chemistry, Gandhigram Institute, Gandhigram, is organizing today webinar on materials for energy, environment, and healthcare applications since yesterday. And three eminent alumni of GRI have already addressed yesterday, and three more I get to do today. I am very happy that I had the opportunity to work with the dedicated faculty of Gandhigram Institute Chemistry Department and had very nice set of chemistry graduates, postgraduates, and researchers. Given the opportunity, the students of Department of Chemistry GRI, they are known to take the challenges in the right sense, and it has been proved today also. With six of our farmer students are delivering lectures today. I am very happy that Dr. Seduraman has taken the initiative, assisted ably by John, under the headship of Dr. Anita Payas and the able guidance of Dr. Sundara Develu, Vice Chancellor in charge of Gandhigram Institute. COVID-19 has resulted in identification of many, not only many drugs, many technologies, and it has contributed substantially in the field of online courses, webinars, etc. for the students community all over the world. I am happy that more than 1,000 students, research scholars, faculty members, not only at the national level, including even the international level, they have participated, and the organizers have to close the gateway for this, for registering this, for this seminar, webinar. I am happy that the students of Gandhigram Institute, who are all well settled in abroad, they have come forward, accepting the invitations offered to them to contribute their might to the chemistry fraternity today. I wish all the participants a very pleasant, meaningful day, and the outcome of this webinar should be reflected in all their endeavors. I am very happy that the Department of Chemistry is doing extremely well and will continue to interact both at the national and the international level in the years to come. Thank you all. Over to Dr. Sevdiraman.
Yeah. Hello.
Yes, yes. Hearing, sir. Hearing.
Okay. So, John sir, can you continue?
Yes, sir. Okay.
Thank you.
Thank you, Professor N.S. Nagarajan, for your blessings. Most respected senior faculty of our department who has guided us in a very, including many funding opportunities and also many conferences. He is the backbone of our university. I'm very much thankful to him for his kind words. And I also thank Dr. Seduraman for his introductory remarks. And also, good morning to all the participants. So yesterday we had a very nice 3 lectures. Of course, there are some technical difficulties. We cannot avoid it. So today, again, we have 3 lectures. The first lecture is going to be given by Dr. Gautaman. He is my own student and he graduated from HKRH College, that is in Uttamapalayam, 2009. Then after completed his BSc degree, he joined in our institute for a PG program. Then immediately after finished his MSc, he joined a PhD. And of course, after finished MSc, he has worked in a school, I should say. That is the reason why there is some 6 years. Don't think that he has took nearly 6 years to complete the degree. Actually, he has worked in a... Okay. So then after that, he also worked in as an assistant professor at
medicine
HKRH College.
வேற கம்பெனி தான் இருக்குமா?
Then after, of course, he worked as an assistant professor for a year. Then he moved to Yangnam University, South Korea, with Professor Sim as a postdoctoral fellow. And he worked there for 1 year. Then he moved to Malaysia, University of Putra, Malaysia, as a postdoctoral research. And till from 2019 to till he is continuing. And he has published 25 papers in international journals with very good impact factors. In fact, in my lab, he started working on graphene and also bimetallic nanoparticle, particularly. He is also awarded, you can see he has got nearly 5 awards, first oral presentation award from different international and national conferences. And he also got the Summer Research Fellowship and a Sakura Fellow. He visited Saha University during 2015. And right now he is working on supercapacitors and also sensor applications at the University of Putra, Malaysia. So once again, of course, in addition to that, he is also helping us many technical difficulties whenever we are facing. And I can say he is also one of the organizers of this meeting. Okay, now over to Gautam. Gautam, please go ahead.
Thank you, sir. Good morning to all present here. So first of all, I would like to express my sincere thanks for the precious opportunity given by Professor S. Abraham John, Professor M. G. Sevduraman, Professor Anita P.S. ma'am, and all the teaching staff. And I would like to thank my sincere thanks to Professor N.S. Nagarajan sir, the former head Department of Chemistry. So today my topic is carbon metal nanocomposites for environmental applications, energy and environmental applications. So first of all, I would like to dedicate this lecture to my guru, co-professor, Professor S. Abraham John. These are the research activities of myself. So initially started with bimetallic nanoparticles fabricated electrodes and metal oxide nanoparticle fabricated electrodes for electrochemical sensing and energy conversion applications, and then moved to anisotropic nanostructures for SCRS applications and electrocatalytic applications. Carbon nanomaterials modified electrodes, since the metal nanoparticles are the costlier one, and we move to the low cost material carbon nanomaterials modified electrode and metal organic frameworks and their composite modified electrodes for electrochemical sensors and of course supercapacitor applications. And finally, the metal nanoparticles and carbon nanocomposites fabricated electrodes for supercapacitor applications, energy conversion applications, and electrochemical sensing of environmental and biosensing applications. The outline of today's topic is fabrication of electrodes with metal nanoparticles, carbon nanomaterials, and their composite for energy conversion applications such as methanol oxidation, O2 reduction in the main part of fuel cell applications, and environmental applications such as electrochemical sensing of environmental pollutants and industrial effluents. So before move on to the topic, a brief introduction about the metal nanoparticles and metal nanostructures. Metal nanoparticles exhibit higher catalytic activity compared to bulk, which is unusual because the bulk material is chemically inert. So generally, metal nanoparticles are synthesized from metal precursor with the help of reducing agent and stabilizing agent. As the size and the shape of the metal nanoparticles changes, the color also changes. This is due to the collective oscillation of electrons in the conductive band, known as surface plasmon oscillation. Generally, the gold nanoparticles and the silver nanoparticles exhibit the surface plasmon resonance in the visible region, whereas the platinum nanoparticles and the copper nanoparticles does not, since they have the weak SPR band. Hence, the size and shape of the metal nanoparticles are the two crucial parameters that can be tailored to alter their properties with specific functions for various applications. Especially, the shape of the nanomaterial offers the versatility in many applications and tuning their property, and hence fabrication of anisotropic nanostructures on conducting substrates has many potential applications in signal amplification, SCRS, and catalysis. Of course, metal nanoparticles are the ideal one for electrocatalytic applications, but their properties can be tuned by combining with the other metal nanoparticle as to form as a bimetallic nanoparticles. The combination of two metal elements as a bimetallic nanoparticles creates the superior property, and the bimetallic nanoparticles have received superior attention because of their extensive use in the field of catalysis, sensing, magnetic, and electronic devices. Bimetallic nanoparticles are in the types of cluster-in-cluster, core shell, and random alloy nanoparticles. In the random alloy nanoparticles, two metal elements are placed in exactly in random, and in the form of core shell nanoparticles, one element forms a core and the another element or metal atom form as a cell to form a core cell metal nanoparticle. Generally, bimetallic nanoparticles are prepared by two various strategies. One is core reduction and another one is successive reduction of two metals. In the core reduction, it is the easiest one two metal precursors were taken, and with the help of reducing agent and as well as the autocatalytic mechanism, the bimetallic nanoparticles were prepared. And in the case of successive reduction, one is formed, after that the another one is. So since the metal nanoparticles are first clear, so we are go with the low cost electrocatalyst such as carbon nanomaterials. Graphene is one of the carbon family. Graphene is a 2D sp2 hybridized sheet and becomes a promising material for electrofabrication due to its distinctive electrical conductivity and high surface area. So generally, graphene is synthesized from graphene oxide, which is synthesized from graphite by Hermes method. So we are nowadays we are using the modified Hermes method for the oxidation of graphite to graphene oxide and exfoliation of graphene oxide to exfoliated GO and reduction of GO to graphene reduced graphene oxide or graphene. CNTs are another type of carbon nanomaterials and are graphene layers rolled into a cylinder of tens of nanometers in diameter to form hollow cylinders of carbon atoms. So generally, the electrocatalytic activity and the electronic properties of the carbon material can be improved by the doping of heteroatom elements, especially nitrogen doping. The lone pair of electrons of nitrogen atom form a delocalized conjugated system with a sp2 hybridized carbon framework, which results improvement in the reactivity and electrocatalytic performance. Graphite carbon nitride.
வீடியோ கால் கூப்பிட்டா
ஏதாவது ஒரு ப்ரோக்ராம்ல பாரு, ஃபர்ஸ்ட் லைனே அதான் இருக்கும். ஆஷ் இன்க்ளூட்
Graphite carbon nitride with a 2D structure has attracted an explosive interest in multifunctional fields owing to its high surface area, chemical and thermal stability, appealing electronic structure, low cost, and eco-friendliness. The graphite carbon nitride expresses good electron donor property, surface polarity, and electronic conductivity because of high nitrogen content, which will enhance the chemical properties. Generally, graphite carbon nitride C3N4 is synthesized from nitrogen-rich aromatic compounds such as melamine by polycondensation process, and the electronic conductivity and electrical property of the graphite carbon nitride can be enhanced by the doping of heteroatom in the lattice of graphite carbon nitride. The catalytic activity of the metal nanoparticles depends not only on the size, morphology, and metallic composition, but also the nature of the substrate where they have place. Under the influence of substrate, the metal nanoparticles exhibit different properties when compared to the free nanoparticles. And the electrocatalytic activity of the metal composite also varies with respect to the nature of the substrate-metal interaction. The graphene oxide, since they have the many functional groups and the graphene oxide can be act as a anchoring sites to incorporate the metal nanoparticles, and the electronic property of the material can be improved by the composite formation. So, carbon nanotubes are also another one type of carbon material, and the composite of carbon nanotubes and metal nanoparticles give the another one property which is superior than the individual one, which is found from the cooperative effect between CNTs and the metal nanoparticles. Even though the metal nanoparticles are the composite were fabricated, were synthesized, they must be fabricated on the solid substrate for the nano device in any form of nano device such as energy devices or sensing devices. Many strategies were followed for the fabrication of the metal nanostructures or nanoparticles on the solid substrate. The first one is self-assembly, drop casting, spin coating, long melt blot jet, dip coating, electroless deposition, and electrode deposition. In the case of self-assembly, with the support of a linker, the metal nanoparticles can be fabricated on the substrate, on the surface of the electrode substrate. The well-known alkyl thiolate gold and alkyl silane gold examples are the known examples for the self-assembly of gold and uh, fabrication of gold nanoparticles on the electrode surface. And electroless deposition, now we follow electroless deposition maximum in our research. In the absence of electric current, we can fabricate the metal nanoparticles on the electrode surface without the help of any reducing agent from the metal source, without synthesizing the metal nanoparticles. Sorry. Sorry for the inconvenience. How to fabricate the carbonaceous material on the electrode surface? The first case is graphene. Graphene, as we know, the graphene is synthesized from graphene oxide and which is synthesized from graphite. Initially, we have to fabricate the graphene oxide by self-assembly method with the help of the linker hexadiamine, and the graphene oxide were assembled on the surface of hexadiamine amine functional group in the form of electrostatic attraction or nucleophilic and nucleophilic addition, and the resultant electrode is employed for electrochemical reduction, which results the formation of electrochemically reduced graphene oxide on the surface of electrode. The electrochemically reduced graphene oxide is nothing but graphene. So we have also another strategies, grafting. We have to first fabricate the amine rich organic linker or heteroatom linker, and after grafting the amino compound, say it is a triazine ring, the graphene oxide were fabricated on the terminal of amine functional triazine ring, and then it undergo for electrochemical reduction. The another strategy is drop casting of graphene oxide on the electrode surface. Of course, we cannot control the thickness and size of the fabricated material in the case of drop casting. And in the case of self-assembly, we can control the thickness of the graphene sheets. The aim of this study is fabrication of nanomaterials for energy conversion applications and environmental applications. The first part is energy conversion applications. So we are mainly focused on methanol oxidation and O2 reduction, which is mainly involved in the fuel cell. So fuel cell is the environmentally friendly energy conversion device from the conversion of chemical energy into electrical energy. So we are focusing mainly on the methanol fuel alkaline fuel cells. So the nanostructured platinum catalysts are mainly employed in the methanol oxidation reaction. And the nanostructured platinum catalysts are well-known catalyst, and depending on the shape and size of the platinum catalyst, the catalytic activity will be varied. So in the methanol oxidation reaction, CO is the main intermediate which strongly adsorbed on the platinum, which blocking the active sites of the platinum catalyst. And hence the platinum poisoning can be observed on the platinum catalyst. Moreover, the platinum does not activate the water below 0.4 volt. So if we want to control the platinum poisoning, the platinum OH bond formation is essential. And in the case of platinum, it is the potential is platinum activation potential is high, and it does not activate the water below 0.4 volt. And hence, the designing an alternate catalyst or modifying the platinum catalyst is highly essential to sort out the above problems. The platinum metal alloys decrease the activation energy of the electrochemical oxygen transfer reaction by two approaches. One is modification of the platinum work function, electronic effect. In this effect, weakening of the platinum CO bond due to the shift of d electrons from the alloy metal to platinum. And bifunctional mechanism, it is a cooperative effect. Here, the metal activates water at low potentials. So as we know, as we discussed already, platinum only do more than plus 0.4 volt. So if we combine with metal, it reduces the potential, and maybe below the 0.4 volt, we can get the metal water activation, and hence it promoting the CO electrooxidation. When combining gold with the platinum as a bimetallic catalyst, the presence of gold in the alloy provides the platform for the oxidation of poisonous CO by changing the electronic band structure and activation energy. The AuOH formation is facile in the Au-based catalyst in contrast to the platinum catalyst. To keep on the mind for the above literature studies, so we prepare the gold platinum bimetallic nanoparticles in the solution form and then fabricated on the electrode surface for methanol oxidation reaction and O2 reduction reaction. So initially we prepared the platinum nanoparticles from platinic acid with the help of the strong reducing agent, sodium borohydride, and then we have added uric acid to the solution to form gold platinum nanoparticles. As we discussed already, the platinum nanoparticles does not exhibit any SBR in the visible region. The platinum chloride exhibit the metal to ligand charge transfer, and the platinum nanoparticles does not exhibit any SBR, whereas the gold nanoparticles exhibit the SBR band in the region of 520 nanometer. And the color of the solution, platinum nanoparticles is brownish yellow, and the gold nanoparticles is brown red, wine red color. So we have monitored the formation of gold platinum bimetallic nanoparticles by the addition of iuric acid to the platinum nanoparticles with the help of UV visible spectrum. So initially the platinum nanoparticles does not show any SPR. After adding the gold iuric acid to the solution color is changed from the brownish yellow to brown color, and we observed a SPR at 530 nanometer. So when we change the mole ratio of gold iuric acid into the platinum nanoparticles, with the formation of gold platinum nanoparticles, the SPR is gradually increased, and at the stage of 1:0.12 mole ratio, it attains saturation. So it follows the galvanic displacement reaction mechanism. So initially the platinum nanoparticles were formed, and the added iuric acid. For the added iuric acid, the platinum nanoparticle acts as a autocatalyst, and it reduced the iuric acid to gold nanoparticles, and the platinum itself oxidized, and the reduced gold nanoparticles were placed inside, and the oxidized platinum nanoparticles were covered the gold nanoparticles to form as a gold platinum bimetallic nanoparticles. And it was confirmed by HRTM images, and the platinum nanoparticles was very spherical particle, and after the formation of gold platinum bimetallic nanoparticles, we can see 2 layers of nanoparticles. Further, the formed gold platinum bimetallic nanoparticles were confirmed by XRD and XPS analysis. So the individual planes of gold and platinum bimetallic nanoparticles from the XRD pattern confirms there is no formation of alloy, but there is a formation of coastal nanoparticles, so that we can get the individual planes. And the XPS also shows the individual peaks of AU4F and the platinum 4F regions of gold and platinum nanoparticles. The EDS line scanning analysis also gives 2 separated lines for platinum as well as gold, means that they were not mixed as a alloy, and they have separated as a gold platinum in the form of core shell nanoparticles. The gold platinum nanoparticles formed nanoparticles were fabricated on the electrode surface with the support of hexadiamine linker, and the gold nanoparticles were modified on the substrate, which was confirmed by the cyclic voltammetry in 0.1 molar of sulfuric acid at 10 millivolt per second scan rate. The platinum nanoparticles fabricated electrode exhibit the hydrogen adsorption and desorption peak with the platinum oxidation and reduction peaks. After the fabrication of gold platinum bimetallic nanoparticles, the fabricated electrode exhibit the gold oxide formation and reduction peak, as well as the platinum oxide reduction peaks along with the hydrogen adsorption and desorption peaks. The hydrogen adsorption and desorption peaks is very particular for the platinum catalyst, and gold oxide formation and reduction is very particular for the gold nanoparticles. So by seeing these 2 responses simultaneously in the graph, we can confirm that the gold platinum bimetallic nanoparticles are successfully fabricated on the electrode surface. The fabricated electrode is utilized for the electrochemical oxidation of methanol for fuel cell applications. Here, the platinum nanoparticles exhibit the methanol oxidation at minus 0.3 volt, and after the formation of gold platinum bimetallic nanoparticles, the bimetallic nanoparticles exhibited the superior catalytic activity than the platinum nanoparticles towards methanol oxidation reaction. And we have compared the synthesized bimetallic nanoparticles with the commercial one. The commercial one shows the methanol oxidation with only 2 milliampere current, and the synthesized Au platinum bimetallic nanoparticles exhibited higher catalytic activity by showing the enhanced oxidation current by 7-fold increased current, and also confirmed that the Au platinum bimetallic nanoparticles synthesized in this method exhibited higher catalytic activity than the commercial platinum catalyst. It also proved from the chronoamperometric studies. So by comparing the other reported papers, the Au platinum nanoparticles exhibited higher catalytic activity in terms of the oxidation potential and the mass activity, as also the increase in catalytic current. It also superior than the commercial platinum catalyst. The next one is oxygen reduction reaction. ORR has involved in wide range of applications such as chemical and biochemical analysis, pharmaceutics, corrosion, environmental conversion, and fuel cells. The ORR kinetics is very slow and sluggish. In order to speed up the kinetics in fuel cell, a cathode ORR catalyst is needed. Preferably, it is a platinum catalyst. Alloying platinum with gold reduces the cost of the catalyst to become economically viable, and hence we utilize the gold platinum bimetallic catalyst for the ORR mechanism. Generally, ORR mechanism follows two directions. One is 4-electron pathway, another one is 2-electron pathway. 4-electron pathway gives O2 to water in the 4-electron transfer. And in the case of 2-electron pathway, the O2 to hydrogen peroxide and then the hydrogen peroxide to water reduction. Here we utilize the gold platinum bimetallic nanoparticles fabricated electrode for the O2 reduction, and the bimetallic nanocatalyst exhibited higher catalytic activity by reducing the onset potential as well as the over potential of O2 reduction, and with the enhanced reduction current. Moreover, for different RPM, we have analyzed with the RDE, and with the help of Kotaki-Lewis plot, we find out it is a 4-electron transfer mechanism, and the mechanism is O2 to hydrogen, water. We also fabricated the gold copper bimetallic nanoparticles without synthesis. In the earlier case, we have synthesized the gold platinum bimetallic nanoparticles in the solution form, and then we fabricated on the electrode surface. In this case, we directly fabricated the gold copper bimetallic nanoparticles without synthesizing the solution form. So here, initially the gold nanoparticles were fabricated on the substrate by electroless deposition with the help of hydrazine as a weak reducing agent, and then the gold nanoparticles fabricated substrate is immobilized on the immersed in the solution containing copper sulfate and hydrazine, and the copper nanoparticles were fabricated on the surface of gold nanoparticles. And the SEM images shows the gold nanoparticles shows very spherical particles in the range of only 60 to 70 nanometer, and after the formation of gold copper bimetallic nanoparticles, it shows some different structures with the elongated rods and flower-like structure. We also confirm the formation of gold copper in the composition with the help of the SEM mapping analysis. So we use the secondary electron detector for the mapping analysis, and here the gold and copper individual shows that there is a formation of gold copper bimetallic nanoparticles on the surface. So we utilize the fabricated electrode for the determination for the O2 reduction reaction in the KOH medium. So in the previous case, we used the sulfuric acid medium. In this case, we used the alkaline medium. So here, the gold copper nanoparticles, bimetallic nanoparticles, fabricated electrode exhibited higher catalytic activity towards O2 reduction reaction when compared to the bare GCE and only gold nanoparticles. The another one case is direct electroless deposition of gold platinum nanoparticles. So in the previous gold platinum nanoparticles, we synthesized the solution. Here we didn't. We directly fabricate the gold platinum nanoparticles from the metal precursor without synthesizing the material. Here, the gold uric acid and GC electrode is immersed into the solution containing uric acid and hydroxylamine, which is a weak reducing agent, and the gold nanoparticles were deposited on the electrode surface of GCE and with the substrate catalyzed electrolysis deposition mechanism. And after that, the resultant electrode is immersed into the solution containing platinic acid and hydroxylamine, and the platinum nanoparticles were fabricated on the surface. So the initially deposited gold nanoparticles on the substrate shows the SPR around 580 nanometer, and after the fabrication of after the reaction takes place for the fabrication of gold platinum bimetallic nanoparticles, the SPR is getting decreased, and at one stage it attains its saturation. The XRD pattern also exhibited, there is no individual peaks, and it is a there is a formation of alloy structure, and SEM image also exhibited the successful formation of gold platinum bimetallic nanoparticles. So from the mapping images, we find that gold and platinum nanoparticles are in the fabricated on the electrode surface. So we utilize the electrode for the O2 reduction. Here, the bimetallic nanoparticles, gold platinum bimetallic nanoparticles fabricated electrode exhibited higher catalytic activity by shifting the O2 reduction potential towards more positive potential and with enhanced reduction current. So by varying the different composition, so at 90-minute deposition shows higher catalytic activity, and with the help of the KL plot, Kotakilevich plot, we find that it is a 4-electron transfer mechanism, and there is a formation of O2 to water. So further, we fabricate the Au platinum nanoparticles on the carbonaceous material, multi-walled carbon nanotubes. So initially the CN multi-walled carbon nanotubes were functionalized, acid functionalized, and then fabricated on the electrode surface with the help of the octane diamine linker and DCC coupling. With the help of DCC coupling, the multi-walled carbon nanotubes were fabricated on the surface of GC electrode. Then the fabricated electrode is immersed into the solution of uric acid and hydroxylamine for the formation of gold nanoparticles on the surface of multi-walled carbon nanotubes, and platinum nanoparticles, and the resultant electrode is immersed into the solution containing platinic acid and hydroxylamine to form the gold platinum bimetallic nanoparticles on the surface of multi-walled carbon nanotubes. It was proven from the SEM images. So multi-walled carbon nanotubes and the Au nanoparticles are very tiny nanoparticles in the range of 60 to 70 nanometer, and after the formation of bimetallic nanoparticles, it shows some flower-like structures, and it also proved from the EDX analysis and line scanning analysis. So the ES analysis exhibited the multi-walled carbon nanotubes gold platinum exhibited higher further, the fabricated material is utilized for methanol oxidation, and the CNTs, gold platinum nanoparticles fabricated electrode exhibited higher catalytic activity. So now, we move to the next part of this lecture, environmental applications. So normally we know electrochemical sensors. So the devices that give information about the composition of a system in real time by coupling a chemically selective layer to an electrochemical transducer is the electrochemical sensor. So different families of electrochemical sensors. One is potentiometric, conductometric, impediometric, voltammetric, and amperometric. So the first one is nitrogen doped carbon nano anions for dihydroxybenzene isomers detection. So dihydroxybenzene isomer is a hydroquinone, catechol, and resacinol. The nitrogen doped carbon nanoanions are synthesized from acetonitrile by flame pyrolysis and condensation at a high temperature, and fabricated on the electrode surface by self-assembly method without any linker. The carbon nanoanions were fabricated on the substrate, and the formation of CNO, the fringes from the HRTM image exhibited, there is a formation of carbon nanoanions. See the layers of onion-like structure, and carbon nanoanions and nitrogen doped carbon nanoanions from the TM images. And from the XPS analysis, we confirm there is a nitrogen doping. So it is not nitrogen doping from the acetonitride. There's a formation of nitrogen doped carbon nanoanions, and the different nitrogen N1S peaks for the different nitrogen moieties confirmed there is a nitrogen doping in the CMOs. So we utilized the carbon nanoanions fabricated electrode for the detection of dihydroxybenzene isomers, hydroquinone, catechol, resacinol. Of course, the simultaneous determination of the dihydroxybenzene isomers. So this carbon nanoanions and nitrogen doped carbon nanoanion fabricated electrode can be able to detect the dihydroxybenzene isomers simultaneously as well as in the real sample analysis also. The next case is the fabrication of gold nanoparticles on the sulfur doped graphitic carbon nitride, and their composite fabrication on the GC electrode for the sensing of atrazine and hydrazine. As we discussed already, the graphitic carbon nitride is synthesized from melamine. So as I want to dope sulfur, so I take sulfur as thiourea as a source for sulfur, and after polycondensation, it forms multi-layers of graphitic carbon nitride. After ultrasonication, we get a single layer of sulfur doped graphitic carbon nitride, and the graphitic carbon nitride is employed for the electrolysis deposition of gold on the surface of graphitic carbon nitride with the help of uric acid and ascorbic acid, a weak reducing agent, and the gold nanoparticles were fabricated on the sheets of graphitic carbon nitride. So the graphitic carbon nitride sheets are very thin layer sheets, and the gold nanoparticles deposition is confirmed from HRTM images as well as the SAED pattern. XPS confirmed the sulfur doping as well as the gold nanoparticles formation on the surface of S-doped C3N4 structure. So we utilize this material for the electrochemical determination of atrazine and hydrazine, and so the composite modified electrode exhibited higher catalytic activity than the individual one. So we also utilize the metal oxide nanoparticles and their composites, the copper oxide nanoparticles for hydroquinone, determination of hydroquinone, and cerium oxide nanoparticle with the Nile blue. Nile blue is electron transfer mediator, the organic linker. It is electron transfer mediator with a enzyme mimetic CO2 exhibited synergetic activity, and we utilize the CO2 Nile blue composite for the determination of hydrazine. In this summary, bimetallic nanoparticles and their composites with multi-wall carbon nanotubes were synthesized by fissile approach and utilized for methanol oxidation and load reduction. Different fabrication techniques were employed for the fabrication of electrodes with nanomaterials. Carbon bimetallic nanoparticle composites fabricated electrode exhibited superior catalytic activity than the individual one. The nitrogen doped carbon nanoanions were synthesized and fabricated on the electrodes for determination of the environmental pollutants and industrial effluents. Graphitic carbon nitride AU nanoparticles nanocomposite exhibited higher catalytic activity towards the atrazine and hydrazine, which are the pesticides used in the agri field. So the strategies followed here could open promising new avenues for designing novel functional materials for energy and environmental applications.
Acknowledgement.
So,
Acknowledgement.
Professor S. Abraham John and research group, Gandhiram Rural Institute, Professor J.J. Sim and research group, Yangnam University, South Korea, Professor Janet Lim Hong Ni and research group, University Putra, Malaysia. Also, the authorities and of Gandhiram Rural Institute and the funding agencies from UGC and DPT. I thank that. Thank you.
Thank you.
Thank you for your patience.
Thank you, Gautam. So I think we have reached almost 11 a.m. So maybe we'll go for 1 or 2 questions. Maybe you can remove your PPT. Okay, any questions?
Any question from Das?
Das, go ahead. Das, go ahead. We can hear it, Mr. Das. You can go ahead. Ajin Das. Yes, Ajin Das, you can go ahead.
I want to know this. Okay.
Any question?
Maybe. Okay. You can ask the questions through his email ID. He will provide the email ID later. Gautam, can you hear me?
Yes, sir.
Okay. So I thank Dr. Gautaman for his wonderful presentation. I know that the time is, of course, if we are given another 10-15 minutes, maybe he'll be very happy. But of course, we have to maintain the time also. So in any case, so I thank on behalf of the Department of Chemistry GRI, I thank Dr. Gautaman for his nice presentation. And of course, most of the participants are asking to share the PPT. Maybe with the permission of the speakers, it may be given to you later, not now. Okay, so the speakers must first, because some of them may feel that the data may be stolen by somebody. So with the permission of the speakers, the PPT may be shared later. Thank you. Thank you very much.
Thank you, sir.
Seduraman sir is online.
Gautam,
Sir?
can you hear me?
Yes, sir.
Thank you very much for the wonderful presentation. There were a few questions. Probably you can go through the chat box. Is there any possibility of allowing AU and PT? That was one of the questions which was asked. Probably you'll be able to reply to them later. And now I think we can call upon Dr. N. Karthik of the Nanjing University, China, to talk on pulsed laser rusted stainless steel as a sustainable electrocatalyst. Now, do we have his profile presentation?
Yes, sir. Yes, sir.
Can you post it?
Just a minute, sir. Just a minute, sir.
Yeah. The Facebook also will be resumed now. There was a problem, and there are so many SMS and then WhatsApp messages to me asking for the resumption of the Facebook relay. I think now that Dr. Gautam is little free, he will try to set it right.
You need time, Gautam, for 5 minutes for Facebook. Maybe we will start after 5 minutes, or you can do it parallelly.
Maybe yes, sir. I will check.
Okay. So let us start the meeting. Okay.
Just a minute.
Karthik has come.
Yes, sir. He is in online.
Okay.
I'll unmute.
As of now, there are about 470 participants attending this webinar. It's very interesting to see so many of them glued. Probably if we had a physical seminar, we will not be able to have this many participants making them available. Of course, I think online platform has enabled all of us to come together. I made it very happy. And we have students from scholars from BHU attending. We have scholars from other parts of country. And I think I could see Professor HSP Rao's name also in the list of participants. And we welcome him on behalf of the organizing committee. And there are quite a few big names among the participants. Now I think we'll go to
his profile.
Karthik.
Just
Just
open. Yes. Next page.
Next. Professor Dr. Nosoyam Karthik did his MSc from Annamalai University, completed his Annamalai University with distinction, and then he completed his MPhil from the Annamalai University. Again, he has done work on NMR, DFT, and hypercolor studies of isomeric alcohols, and then he completed his BHT from Gandhigram Institute under my guidance. He has worked on sol gel and superhydrophobic coatings for the protection of metallic surfaces, and he has got a good number of publications. He was a very sincere, hardworking student. He was almost minding his business and doing nothing else. To that extent, he was a serious research scholar, and he was working in Rajalakshmi College of Engineering, Chennai, from June 2010 to 2012, and then after completing his PhD from Gandhigram Institute, he went abroad. He was actually a postdoctoral researcher in the School of Chemical Engineering, Yangnam University, South Korea, and he was also working in Savita College of Engineering for some time, and he was also working in Munuadi College of Engineering, if I remember right, for some time, and then he was again in Korea for a short term, senior researcher at the College of Engineering, Kangwon National University, Samcheok, South Korea, and now he has moved over to the Nanjing. Okay, he is now the postdoctoral researcher at School of Material Science and Engineering at Nanjing, and at Nanjing, China. Probably that is little away from Wuhan, and where this COVID-19 originated. And next page. His research appreciation. Independently, he designed a screw-type working electrode, which finds extensive application in surface characterization, electrochemical analysis. And in fact, many of the labs in India are following this kind of working electrode, which he has designed. And he has more than 25 peer-reviewed scientific publications. And H index is 11. And he has got 3 awards, 2 for the best oral presentations and 1 for the best poster presentation in all the 3 international conferences. And some of his papers, for example, in sustainable energy and fuels and Langmore are the best publications. He has had a paper in fuels also. A distinguished researcher, a good human being, a very person with helping tendency, kind of go well with the team members, and in fact he is an asset to the institution, and he was working with me in the BRNS project, and his paper on the superhydrophobic coating really paved way for several other PhDs also. So with this brief introduction, now I request Dr. N. Karthik to make a presentation on the topic pulse laser rusted stainless steel as a sustainable electrocatalyst. Over to Karthik. Karthik, you can start. All
Yes.
others can mute. And there is a provision for, I think, protecting your slides. Probably Gautam will tell you. Gautam?
Yes, sir. Yes, sir.
Yeah, yeah. Tell him how to protect. Otherwise, people will start scratching.
Okay. So maybe Dr. Karthik,
Yes, please.
can you please share your slides?
Yeah.
Just I stop my sharing and you can.
Yeah,
share.
you please you sign out yours.
Yes.
I will start sharing. I think you have to disable your screen sharing.
Yes, you can now.
Yeah.
So in the top of your presentation,
Yes.
there is one option more,
Okay.
and then disable attendee to annotate.
Already started.
Disable participants annotation. Is it?
Yes.
Yes,
And
yes.
now close
Okay,
the
fine.
screen and do it again.
Oh,
Okay. Close your screen and share it again, please.
Already somebody started.
Yes. Sir. Please share your screen.
just a minute.
Please check once again the option, attendee annotation.
Yeah, it is disabled.
Okay.
Okay,
Thank
okay,
Yes.
fine.
you. Thank you.
Yeah, fine. Thank you, sir, for a wonderful introduction about my career as well as the personal things. And first of all, I thank the convener and the co-convener of this international webinar, and also extend my sincere gratitude to the rest of the faculty members in the Department of Chemistry and authorities of GRI who gave this opportunity to present my work in my home institution, that is in GRI. So it is very proud to present my work in front of my teacher, friends, colleagues, and students. Now I move on to my topic, which is on the pulsed laser rusted stainless steel as a sustainable electrocatalyst. The outline of the presentation is as follows. The first topic is under the heading of hydrogen economy, which is nothing but nowadays 90% of our daily energy needs are fulfilled by means of hydrocarbon or fossil fuel economy. But due to the rapid emission of carbon dioxide, one kind of greenhouse gases, global warming is also simultaneously increasing. So in order to find an alternative source for this unenvironment friendly fossil fuel, the researchers are turned around towards the low carbon energy source, which is clean fuel, that is hydrogen. The production of hydrogen from the eco-friendly natured material is known as hydrogen economy. This diagram represents that how many number of hydrogen powered vehicles are going on the road. Till now, we have only 80,000, 81,000, but by 2040, it will increase up to 620 million. And also, respective charging stations are very low, Right now we have only 310, whereas by 2040 it will increase up to 1200. And many industry as well as household appliances will be based on the fuel cell batteries because they have much energy storage and capacity. But the major obstacle in the hydrogen storage and the transport is, so we need to choose a material which overcome these kind of drawbacks, that is transport as well as storage, and also it must produces enormous amount of hydrogen. There are various techniques are available to produce hydrogen, but the eco-friendly as well as the prominent techniques are water splitting. Water splitting is nothing but splitting water into hydrogen and oxygen. That is, hydrogen evolution will take place on the cathode and oxygen evolution takes place on the anode. So this is a electron transfer reaction. So these come under electrocatalysis. Electrocatalysis is nothing but which is the combination of oxidation and reduction reactions through the direct transfer of electrons. So electrons plays a major role in the electrocatalysis. And what is the role of electrocatalyst? Electrocatalyst must lower the overpotential of the reaction. What is meant by overpotential? Overpotential is nothing but the difference between applied potential and standard potential. So the good electrocatalyst means it must lower the overpotential, or in other term, it must possesses very low overpotential. But it has some limitations. That is, its stability is very poor and its reaction rate is hindered by means of applied potential and standard potential. And due to its poor stability and multi-electron transfer, its reaction rate has been reduced. That is sluggish kinetic reaction. For example, ORR. As previously Dr. Gautaman told that ORR is sluggish kinetics, which also hindered the efficiency of an electrocatalyst towards water splitting. So we need to fabricate an electrocatalyst which possesses low overpotential and high stability with less entrance from the side reactions. The third one is on the Tafel slope. Not only the electrocatalyst must possess low overpotential, but also it must have low Tafel slope value. So what kind of information we can get from the Tafel slope means we can able to determine the reaction mechanisms and how much of current has been exchanged between the electrodes. Through this, we can able to determine the catalytic activity of an electrocatalyst. So how we can determine this Tafel slope? By means of polarization curves. This is an example of a polarization curve which consists of many regions, but which point will be suitable for the Tafel slope measurement means the kinetically controlled region, that is the slow rate step, that is the rate determining step points are considered as an kinetically controlled region which are chosen for the evaluation of Tafel slope using the Tafel equation, which is eta equal to A plus B log J. Eta is the overpotential, A is the intercept, and B is the Tafel slope, and J is the exchange current density. If you extrapolated in the kinetically controlled region of anodic Tafel region, you can able to determine the OER reaction mechanism. Whereas if you extrapolated on the cathodic Tafel region, you can able to determine the HER reaction mechanism. So the good electrocatalyst means it must produce enormous amount of hydrogen, and also it must be used for the transport as well as the storage capacity with low overpotential and low Tafel slope. Next one is how to fabricate these electrocatalysts. There are various strategies are available to fabricate the electrocatalyst. Among these, laser surface engineering finds extensive application due to its flexibility, scalability, and chemical-free protection through which modifies the topography, chemistry, and wettability of the base material. This pictorial representation for the laser beam interaction with the material surface. When the laser beam is irradiated on the metal surface,
Thank you.
the metal atoms present on the bulk of the material get activated due to its high temperature activation and redeposited over the surface. So we can able to make different kind of texture patterns. For example, dimples, grooves, line, any kind of patterns we can draw over the metal surface. What will happen when a laser beam is irradiated over the metal surface means, which is nothing but a rust, that is corrosion is happening there. For example, if a stainless steel or mild steel is irradiated by means of laser beam, the dark intense rust layer is formed over the metal surface. In olden days, we think that rust is the worthless thing, but nowadays they are seen as an advantage in many fields such as botanics, tribology, and energy. So for this reason, we utilized laser surface engineering in our study. How we did this? This is the experimental section. So 316 stainless steel with the size of 1:1 has been pre-treated with different grades of emery papers and ultrasonically cleaned in ethanol and water for 10 minutes. As a result, we get the pre-treated or pre-cleaned stainless steel substrate. That is the bare one, which is abbreviated as BA or SS, which implies the bare without any modification. When the cleaned substrate is subjected for the ND-YAG pulsed laser, it is ND is neodymium, Y is yttrium, A is aluminum, G is garnet. So when it is subjected to the pulsed laser with an wavelength of 1064 nanometer with a pulse energy of 20 millijoule, it gets textured by means of honeycomb. Honeycomb texture has been drawn over the one side of the stainless steel. Then resulting substrate is abbreviated as SSL, or it is the expansion is single side laser rusted stainless steel. When it is irradiated on both sides, that is double side, it requires 6 minutes 32 seconds. Whereas for single side irradiation, you need 3 minutes 16 seconds. Whereas for double side irradiation, you need 6 minutes 32 seconds. So that resulting substrates are termed as DSLR, that is double side laser rusted stainless steel. So here we are using two kind of substrates. One is single side irradiated and another one is both side, double side irradiated substrates. These substrates are subjected to the surface analysis such as XRD, XPS, SEM, EDOX, 3D, and contact angle. And further, it is evaluated for its electrocatalytic behavior through electroanalytical techniques such as LSV, CV, and EIS in 1 molar KOH solution. This slide shows the same 3D and contact angle of the bare, single side, and double side laser rusted stainless steel. Figure A is corresponding to the bare stainless steel, which consists of smooth surface with the gray silver color. Whereas when the pre-cleaned stainless steel is irradiated on single side, the perfect honeycomb texture has been drawn over the substrate, and which is confirmed visually through the formation of light brown colored layer, that is, which is nothing but rust. That is, the main constituent present in the stainless steel is Fe, which undergoes the oxidation to its oxides. When the substrate is irradiated on both sides, the intensity of the brown color is increases. That is, dark brown rust layer is formed over the substrate, which confirmed that thick or dense rust layer or oxides of iron, nickel, and chromium is formed over the surface. Then DEF or the respective 3D images of the substrates. when we look this, the surface roughness is increasing from 0.2 to 12.1. So when we irradiated the metal surface by means of laser, the surface roughness will also increases. Simultaneously, the wettability is also increasing. We can see from figure G that it is respective for the bare stainless steel substrate whose contact angle is about 29 degree, whereas for single side it is about 2, whereas for double side it is about 1. So laser radiation is useful for the creating rough texture as well as for the super hydrophilic texture. Next one is EDS analysis. So the as fabricated laser textured material has been subjected for EDS analysis. From this graph, we can able to determine or identify that the concentration or percentage of oxygen is increasing, which is highlighted in the red box. So we can see from figure A, that is bare stainless steel has only 8% of oxygen, whereas single side and double side has nearly same, that is about 38%. So the oxygen percentage is increasing, which reveals that during laser radiation, oxidation is takes place. Simultaneously, the concentration of chromium and nickel is decreasing, which shows that the atom present in the crystalline package in the bulk get redeposited over the over the surface, and which are undergoes oxidation to a multivalent oxides. The formation of these multivalent oxides are confirmed through the XRD and XPS analysis. Figure A is for the XRD analysis. We can see when compared to bare stainless steel, single side and double side laser arrested stainless steel possesses a new peak or XRD pattern around 44, which is respective to the ferrite. That is, ferrite means it is the magnetic behavior oxide of the steel, whereas bare consists of only austenite. Austenite means it is less magnetic behavior element. So when we irradiated the stainless steel by means of laser, the magnetic property will also change, which plays an important role in the water splitting. Further, the binding energy of the as formed oxides are confirmed through XPS analysis. From this spectrum, we can able to confirm that the percentage or the binding energies are shifted towards a higher energy region of oxygen, nickel, iron, as well as chromium. Table 1 represents the Fe2P 3x2 spectral fitting data. Here you can see the differences. Major difference is when compared to bare stainless steel, this laser textured stainless steel possesses higher oxidized ions, that is Fe3, that is Fe3 oxyhydroxide. More number of 3-valent ions are formed over the single as well as double rested stainless steel. Likewise, chromium, the chromium 6 oxide, higher valent oxide is formed only on the DSLR, that is double side laser rested stainless steel. Table 3 also shows that nickel 3 plus is predominantly formed in the case of double side laser rested stainless steel, which is further supported by means of OAS spectral fitting parameters. From XPS survey spectrum as well as the table, we confirmed that during laser radiation, high valence ion chromium and nickel oxides are formed over the surface. This is the cyclic voltammogram, which is recorded in the non-Faradaic region, because through this only, through non-Faradaic region only, we can able to determine the electrochemically active surface area, that is directly proportional to the double layer capacitance. So if double layer capacitance is high, means definitely electrochemically active surface area is also high. If electrochemically active surface area is high, means definitely it must possess high electrocatalytic activity. So figure A is for bare, figure B is for a single side, C is for the double side laser rusted stainless steel. From the graph itself, we can determine that Figure A, the current density is about 0.036, whereas here it is moved towards the positive region, and also for double side, the current density is also increasing. This slide shows the OER, oxygen evolution reaction of the as fabricated electrodes. Figure A is the linear sweep voltammetry curves of bar, single side and double side laser rusted stainless steel. So it's a one kind of fuel cell reaction, as Dr. Gaudaman said in the earlier presentation. So it's a one kind of fuel cell reaction. The fuel cell reaction output, minimum output is about 10 milliampere. So all the three electrodes achieved that. But among these three, the double side laser rusted stainless steel achieved very low over potential of about 382 millivolt. So using this and extrapolated on the kinetically controlled region, we can able to determine the taffel slope, which is depicted in figure B. Again, among these three, the double side laser rusted stainless steel exhibits low taffel slope of about 52 millivolt per decade. Here, the potential scales are converted into RHE scale, that is reversible hydrogen electrode scale. Why means? Because all other references electrode are pH dependent, while the reversible electrode is of independent of pH. That's why we are expressing in terms of RHE scale. Figure C is for the calculation of double layer capacitance using the following equation. CDL equal to JDL divided by nu, that is current density divided by the scan rate. Here also we achieved the same trend, that is double side laser rusted stainless steel exhibits a higher double layer capacitance of about 351 microfaraday per centimeter square. Using this double layer capacitance, we can able to determine the roughness theoretically using the formula RF equal to CDL divided by CDL dot, which is nothing but the smooth surface double layer capacitance. For example, the smooth stainless steel has 30 microfaraday of double layer capacitance. This is the experimentally calculated one. Again, the double side laser rusted stainless steel gives high exchange current density as well as the roughness value. Figure E shows the electrochemical impedance spectroscopy of the as fabricated electrodes. It is clearly seen that the Nyquist loop or semicircle is high for the bare stainless steel, whereas for single it is reducing. For double side it is further reducing. So once the semicircle is reducing means it implies that charge transfer resistance is reducing, simultaneously double layer capacitance or conductivity is increasing. In addition to that, all the three Nyquist plots shows a low frequency, that is an inductive loop at the low frequency, which is highlighted by means of a red line, which is arised due to the magnetic behavior of the materials. So the bare stainless steel also has magnetic behavior, but after laser radiation, its magnetic behavior is enhanced. And figure F is for the long-term stability test, that is chronopotentiometric curves, which is recorded at a constant current of about 10 milliampere, because that is the fuel cell output current. Here, initially the over potential is decreasing up to 2.5 hours. After that, it starts to increases and attain a steady state. Why it attains a steady state before that? This zigzag motion is happening means because of the polarization. That is, the surface oxides undergoes polarization up to 2.5 hours. After that, the polarization is stopped, so it reaches the steady state. From this, we concluded that there is no correlation between the activity and stability of the electrocatalyst. And what kind of motivations we can get from this work means we need to redesign the conventional materials at micro nano scale to fully exploit its electrochemical activity through the laser texturing. So these textured material will able to store high energy and which will be used for the future use. When we utilize these kind of laser textured material for hydrogen production, we will get enormous amount of hydrogen, and these produced molecular hydrogens will reduces the carbon footprints. And also we believe that the proposed strategy will fulfill the requirements of the hydrogen economy. And this is our eminent team, Professor M.G. Seduraman. As Eli told, he is my PhD mentor. During my PhD, I thought that why we are working on corrosion, because so many various other fields are available at the time. But now I realize why we worked on corrosion, because fortunately I can able to expand my research domains in various fields like corrosion, superhydrophobic, or tribology, or biomedical, any other things. So the basement is developed by Professor M.G. Seduraman. I thank for his guidance. And Dr. Jabakumar, he is now working as a research professor in Yangnam University. He is one of the backbone for my research activities. Well-wisher too, and extend my thanks to Professor Zion, who is the current my postdoctoral guide working in Nanjing. Such a kind human being. He encouraged a lot and he helped me a lot to stabilize this laser surface engineering works. So I extend my thanks to all my colleagues. Thank you for your active participations. Thank you, one and all.
Thank you, Karthik.
Thank you, sir.
Yeah, is there any questions from the audience on that? Okay, so it was nice hearing you again. Many people are asking for the PPT and all that. So I hope you'll be able to share after the webinar is over. Thank you once again on behalf of the Department of Chemistry. So I think I hand over again to Gautam for the next talk. Gautam, please. Mr. John?
Yes, sir.
Okay, sir, take over.
Okay. Gautam?
Yes, sir.
Okay. So the announcements, I think now it is on YouTube. Maybe you can tell, Gautam.
Yes, sir. So due to some technical issues, we cannot live with the Facebook. So please follow the YouTube link, which I have given in the chat box. You can share it to your friends, those who need the Facebook link. So you can share the YouTube link instead of the Facebook link. Okay, thank you.
Now it is Muthu
Next
Prabhu's turn. Has Muthu Prabhu come online?
Yes, sir. He is online, but just 2 minutes, sir.
Okay. Oh, Muthu Prabhu is there. Good. So singer மாதிரி ஹெட்ஃபோன்லாம் போட்டுருக்கு.
ஸ்டீரியோலாம் வச்சிருக்காரு போல தெரியுது.
I thought he is going to come out with some music also.
The Meenakshi madam is online. Gautam?
Just I will check, sir.
Meenakshi,
I'll check.
Meenakshi madam, if she is online, we will ask her to introduce Muthu Prabhu.
Okay.
Well, he is giving it from the department, huh?
Madam is in online, sir, but
Okay.
couldn't connect with the video.
Anyway, okay, no problem.
Just a minute, sir. I will prepare the slides for Dr. Muthu.
Probably we would have informed earlier.
We could have.
Right. Yes.
Our Vice Chancellor in charge, Professor Sundarodilu, is there with us. We have Dr. Anita Paes, head of the department, and a host of other faculty members from the neighboring institutions. A big long list is there, so I welcome once again on behalf of the Department of Chemistry all of you. And,
Madam is there.
yes, come.
I'm here. I'm holding my grandson.
Madam, can you introduce your student, madam? Is it possible?
Oh,
Yes.
of course, it's my pleasure. But anyway, you please introduce. No problem.
No, if possible, you can do it, madam. Maybe you give it to your grandson to somebody else.
Wow. He's making his result.
Yes, you can
Gautam, you can
display his
Uh,
resume.
maybe
any problem?
yes, I will share the.
Okay. We will wait.
I think you have to unmute yourself, Gautam. I mean, Prabhu, Muthu Prabhu. There is a provision to block the scratchings also. Are you able to hear us, Muthu Prabhu? Dr. Muthu Prabhu, are you able to hear me?
There is a noise from Muthu Prabhu.
Yeah. He doesn't keep quiet, makes noise, huh? You have muted your mic.
Introduce பண்ணுங்கங்கறாரு. அவனை பத்தி எதுவுமே தெரியல.
இல்ல இருக்கு. மேடம் இருக்கு, எங்க கையில இருக்கு.
We have, don't worry. You are on. What you are speaking is you are able to hear. Is it okay?
Wait.
This is going to become the order of the day. Future, for at least for 2 years, we may not be able to have any seminars or conferences, and probably the big business of Shanghai holding the conferences will probably become a no affair from now on, and webinar is going to be part of the game. And I'm sure that there will be many more conferences by many institutions connecting people through webinar, discussing things. So one-to-one, face-to-face meeting is going to become the thing of the past, and it's all going to be through net and through web. We are going to have, and I do not know whether we will be able to have 90 hours of teaching and all that, with UGC and ministry saying that we should have only 60 to 50, 60 hours through face-to-face and rest through online. I think with social distancing and all that, this is very convenient, whether it is COVID-19 or any other virus that is coming, to keep ourselves safe. I think this is the best of the option. Now, can we have?
Now somebody else doing something.
Yeah. They have posted.
Somebody has Syed
Jamal Muhammad. Anyway, there should be provision for this also.
So can you see the slides, sir?
No.
Yeah, it is there. Yes.
Right.
So it's a pleasure to introduce Dr. S. Muthu Prabhu, postdoctoral research fellow. Is Dr. Meenakshi there?
Gautam, address, there is some mistake. He is not University of Putra, Malaysia. You changed it. Okay. Copy paste.
Yeah, presently he is I think there is copy paste problem.
Madam is there?
He is presently with Alagappa University, Karaikudi. He has done his BSc.
Madam is available, I think.
Madam,
Madam?
No,
Ah.
no, no.
Yes.
எனக்கு என்ன
Madam?
பண்ண தெரியல.
Yes.
Hello.
Madam, you can go ahead, madam.
Sir, I'm holding my grandson.
It's
You
okay,
please
madam.
introduce
Okay.
him.
So,
Okay.
he has done his BSc and MSc from Gandhigram Institute, Deemed University. So PhD is again from the same university under the able guidance of Professor Meenakshi. And he has done his work on defluoridation of drinking water using synthetic and biopolymeric assisted materials. And after finishing his PhD, he moved over to Yonsei University, South Korea. He worked under Professor G. Lee on zero valent ion materials for dye adsorption. And later on, he moved over to Kyushu University with a prestigious JSPS award. And in fact, he has published quite a good number of articles, and his main focus of area was on the synthesis and surface modification of 2D metal organic framework and the graphene-based materials for noxious ions removal. And he was also, later on moved over to Goin Peak National University, South Korea, as a research professor. And during his tenure at South Korea, he focused on photodegradation of organic molecules using MXenes. So presently, he moved over to, he's a postdoc at Alagappa University. He's working as a supercapacitor using functionalized 2D materials. So he's a senior postdoctoral fellow at Alagappa University, and he has nearly 35 publications with the H index of 15. And he has filed 3 Korean patents also. A distinguished researcher, a very active researcher, I would say. I still I'm reminded of his days as a student, where he used to be a very enthusiastic student, interacting with everybody. And he has received many awards, both best oral and poster presentation awards from international conferences. He received awards like RUSA Senior PDF, JSPS, and Dr. Kothari Award. And he was selected as one among the 15 Indian researchers to participate in IGCS Winter School for Sustainable Water Management in Urban Areas, conducted by Indo-German Center for Sustainability. And he is also recognized as a potential reviewer for many journals. And his articles in the International Journal of Macromolecules is a widely cited article. And so a distinguished academician, and he used to maintain excellent relationship with all his teachers and his peer lab members. And I still remember Professor Meenakshi recalling his work even now. So that is the kind of impression he has left behind on the teacher and on the colleagues in the department. So it is a pleasure having him here. So we welcome him to India, and having joined Alagappa University, I'm sure that he'll be able to contribute much more than what he had done when he was in abroad. So thank you, Muthu Prabhu, for accepting our invitation at a very short notice. So it is your turn to deliver the lecture. So I again wholeheartedly welcome you, and then request you to continue with your lecture. Thank you. Thank you for accepting. Thank you for coming forward to deliver the lecture. You can start, Muthu Prabhu.
Yes.
Muthu Prabhu?
Yes, he is available.
You tell him how to avoid the scratch and all that.
Prabhu?
So audio has some problem. Prabhu is there?
No, sir, I'm searching him.
I think he is there, but I have some problem with the audio.
Name is, I think, different.
Maybe you call him over phone. What is doing? Gautam? Whether he is available or not.
No, sir. Do you have his number, sir? Actually,
I have his number. I will call him.
okay, sir.
Okay.
Hello.
அவன் அலோ பண்ண சொல்றான்.
Hello.
ஒருவேளை எல்லாரும் உள்ள போட்டாங்க.
Kindly bear with me for 5 minutes.
அவனோட வாய்ஸ் கேட்கவே இல்லை. ஒரு மாதிரி இது மட்டும் தான் வருது. அந்த இதுதான் வந்தது.
We'll be able to get Muthu Prabhu connected. There is some connection issue Professor John is trying to address, and we'll be able to have him reconnected in another 2-3 minutes. And for the information of the participants, some of them have said that there is some problem with giving their feedback yesterday. We will try to sort out the issue, and today's feedback also will make it available so that you can fill it up and then send it to us. And one small request for the participants: please do not pester for the certificates immediately, because we have more participants and we may probably have to prepare the certificates and all that. It will take some time. So probably before first week of June, we'll be able to send you all the certificates. So that is one thing. And regarding the PowerPoint presentations, we are requesting all the speakers to share with them, and with their consent, we'll be able to send you once they tell us their consent. That is one of the things that I just wanted to inform you. And is he able to get? So these are all the issues that you come across in webinars. Of course, it's unavoidable. Kindly bear with us. I hope he'll be able to come. Somebody has written, thank you for telling about the certificates. I have not received the yesterday something. Anyway. So Guhanathan from, I think Vellore has joined us. I'm very happy to see him. Professor Guhanathan?
Hello, sir. கேக்குதா sir?
Now it's okay.
Okay, thank you, sir. Sorry for the inconvenience.
Are you able to hear me?
Yeah, yes, sir. I'm hearing.
Okay, go ahead. It's nice having you back again, Muthu Prabhu.
Thank you, sir.
Okay,
Sorry.
fine.
Sorry for the inconvenience.
Okay, no problem. Go ahead.
So, I would
You're
like
able
to.
to share?
Yes, sir. Now I will share my screen.
Yeah.
Okay. Hope my slides are visible.
Do you know the annotation?
Yes, I know the annotation.
Okay. Then it's okay.
Okay.
Disable the attendee to annotate.
Okay.
Okay.
Thank you for your kind. Thank you for your kind introduction about me. Brief introduction about me. Good afternoon to everyone. Good afternoon to everyone. First, I would like to thank the organizers of this COVID-19 international webinar, especially to the conveners of program, Professor Siddharama sir and Abraham Jan sir, and other department faculty members. Of course, they are all my teachers, and for giving me an opportunity to present my work as well as sharing my experience on this particular topic. So, okay. So now, hope my slides are visible to everyone. I'm going to introduce a new topic called mixins. Mixin is nothing but is a two-dimensional structure material. And the "-ine" suffix "-ine" comes from the graphene. Since the behavior and properties are similar to the graphene material, so the name was fixed as mixin. And it is quite new to the India. The most of the people are not aware of this material, and a few groups like in VIT and some of the IITs people are working on mixing material, and it's quite popular in US and as well as in South Korea. So I thought this mixing material will be useful to the youngsters like me. I'm also is quite new this topic, and recently we are working on it. So in this slides, I would like to focus on how the mixing materials are differ from other 2D materials, and how the material was synthesized, and what are the properties of mixing materials, and the applications towards energy as well as environment. I would like to focus on it. Before entering into the subject of mixing, I would like to explain some of the how the nanostructure materials are defined. Before my talk, there are several speakers have already explained what is nanomaterials and how the nanomaterials are useful for energy as well as environment. But I would like to briefly explain how the nanomaterials are designed, fabricated, and they're defined. The nanomaterials are nothing but is a particle whose size in the range of 1 to 100 nanometer, respective of dimensions considers. A couple of Ukrainian scientists, Glater and Strohard, have defined this. Initially, they defined fluorines is a zero-dimensional, and nanotubes and nanowires are one-dimensional, and nanoflowers are two-dimensional structures. But after several years, they thought the definitions was wrong, and in 2017, the Ukrainian scientists reported the modified forms of nanostructured materials. For example, if your material has all the 3 dimensions are nano-sized, then it will be a nanomaterial. Is the best example is quantum dots. Then, if the material has 2 dimensions are nano-sized, then it will be nanotubes. For example, the better example is nanotubes and nanowires. Then it is called one-dimensional. Then, if the material has 1 dimension is nano-size and other than the other 2 sides, then it will be like a sheets, like a paper. Then it's called 2-dimensional structure. The best example of 2D dimensions are graphene. the known example, the popular example is graphene. And there is, if a material does not have any dimensions, then it will be a 3D structures, and the best example is carbon fluorine. Then mixin is categorized under as a 2D materials. Then I would like to focus on 2D materials and the properties of 2D materials, how they synthesized from the 2D materials. Okay, 2D materials are the substance with a thickness of few nanometers or less than that of, and graphene, layer double hydroxides, metal dichalcothiones like molybdenum disulfide, and carbon nitrates and the boron nitrates. These are the beautiful examples of 2D materials. And the mexine is also incorporated into the family. So we can also say that mexine is also a 2D material. And the special properties of 2D materials are high surface area and highly active sites on the edges. And it is highly disposed in all the medium like aqueous and as well as environmental medium. And it also acts as a supporting material to form the nanocomposite and nanomaterials. And also it acts as a host material to welcoming the new guest materials to make it the nanocomposites. And it can be tuned by the electronic structure by doping of some heteroatoms or the nanoparticles, and the interfacial interaction was much higher than the other materials. Also, the intrinsic activity and the atomic thickness are quite impressive than the other materials also. Basically, popularly, there are two methods are available to synthesize 2D materials. One is top-down approach and another one is bottom-up approach. Top-down approach is nothing but it starts with the bulk material and make it the thinner. Then the latter case starts with the atomic ingredients and assemble them together. These are the two methods are commonly adopted for synthesizing 2D materials. For the top-down approach, there are two main methods are available. One is mechanical exfoliation and another one is chemical intercalation. Mechanical exfoliation is nothing but sticky tape was applied on the surface of bulk material, then it's peel up, then it get exfoliated of a few sheets of nanomaterial. Then it converted into the nano sheets by washing and other several as usual methods. Then in the form of chemical intercalation, the layer double hydroxide materials was introduced into the nanomaterial in between the layer, the basal planes. Then it get exfoliated first, then it will easily delaminated form of nanosheet will be obtained. And for the bottom-up approach, there are two methods. One is CVD growth and another one is molecular cell assembly. Molecular cell assembly is nothing but using the surfactant molecule to get the self-assembled layered of material, then it will get further delaminated easily. For the CVD, it's using the vapor deposition method, then we can easily delaminate from structures, bulk structures. From the CM images shown in the right side of this image, this part, you can see the all the method has different structures, which is not easily described from each other. So the every method has own advantages as well as disadvantages. Okay, what is mexine? Why mexine is needed? Mexine is a 2D transitional metal carbides. It's known as mexine. It has the layered hexagonal structure, and the mexine, the suffix in emphasizes. Yes.
Sorry, the slides are not moved. Make sure the slides are moving.
Now, okay.
No.
Okay.
You just press F5. Press F5, please.
Yes, yes. Okay.
No, it is not moving.
Why my screen is fast? I don't know.
You just restart your sharing, please.
Okay. My screen is not sharing well. Okay. I will share again.
Okay.
Okay. It's okay.
Next.
Is it okay?
No, it is not moving.
Wait. Sorry for the inconvenience. Shared window is closed. Okay. Okay, I will do it again. Is it okay?
Next slide. Yeah, it's fine.
Okay.
Okay. Sorry.
Okay, sorry for the inconvenience again. Mexin is nothing but it's a 2D materials. As I already said, it has the layered hexagonal structure of metal carbides and metal nitrides. The mexin in, the suffix in to emphasize the similarity to graphene. Hence, the in is comes from the graphene material. There are more than 60 phases of mexin material was obtained. Most of them are titanium background and chromium, vanadium, and neodymium backgrounds, which exhibit properties like high chemical stability, high electrical conductivity, and environment-friendly characteristics. It has hydrophilic in nature and abundant and highly active functional groups on the surfaces. The mixing materials is similar to the an instrument called accordion. This is the portable form of piano. We can say that it easily play with the help of air. So most of the papers are coming from the title of accordion-like the images are accordion-like materials. So we can also say that the mexin is similar to the accordion instrument. So this accordion material. So this Professor Yuri Kowarski, who discovered the new family of two-dimensional materials called mexins. He is from Ukraine scientist. He is the associate editor of ASIS Nano. Then he discovered and described a new forms of carbon called canonical and polygonal crystals. He was also named as one of the world's most influenced minds list by Thomson Reuters, Canadian corporation limited. Also, he has done conduct the hydrothermal synthesis of carbon nanotubes and showed the anomalous slow movement of water in a functionalized carbon nanotubes by in situ micron electroscopy. This study ultimately lead to development of nanotubes, deep single cell probes. Okay. How the mexin material was synthesized from Max phase? Okay. Initially, they started with many methods, but this method is mostly adopted for the synthesis of titanium-based max phase. Initially, they started with 3:1:2 ratio of elemental titanium, aluminum, and graphite-based material was ball milled for 48 hours. Then the powder form of this ball milled material was applied to the pressure instrument to make it a cylindrical disc with size of 50 millimeter diameter and 10 millimeter height. Then this disc was further treated with tube furnace for about 1730 Kelvin for 1 hour with under argon atmosphere. So the obtained maize powder was titanium aluminum carbide, and this is the raw material for mexin. This is a bulk form as shown in here the left side of image. Then this max phase was immersed in 40% HF at 313 Kelvin for 10 hours. Then we can get the final product was washed and dried and the freeze dried. Then we can get the aluminum removed pieces. The advantage of HF was to remove aluminum phase to get the exfoliated sheet. That means the bulk phase has aluminum layer. The aluminum layer to be selectively removed from the max phase to get the wide reach or the expanded structure of mexin. When the aluminum etching was removed and it was calculated, the aluminum concentration was analyzed using ICP-ES to get the quantitative amount of mexin material was obtained. Then this is the schematic representation of mexin phase was derived from the max phase. It was selectively removed, and you can see the bottom up the bottom image. The HF was selectively etched, and the introduction of new functional groups like fluoride and hydroxide on the surface of mexin, which is highly useful, which induce the hydrophilic in nature. You can see here. you can see the some images of some images of Max and Maxine, and it was confirmed by TEM image also. Gautam, how to control again? I cannot do it here. Disable participant annotation, right?
Yeah. You just go to the top and more option.
Okay. Disable.
Attendee to annotate. Disable attendee to annotate.
Disable. Okay, I already did.
Okay.
Now, why Maxine? Why not graphene? Graphene has, we know that graphene has a van der Waals interaction between the layers, which is, but in the case of Maxine, which is much stronger than the graphene oxide materials, then it exhibit higher electrical capacitance, is more flexible than the graphene material and more stable, and can easily prepared. It can easily be prepared and more moldable form of Maxines than the graphene oxides compared to other form also. Then this material can work both energy as well as environmental sites. For the energy sites, this mixing material was applied to electrical energy storage devices like pseudocapacitors, lithium-ion batteries, and hybrid devices. And also, it's working for some energy obligations. And it is also focused on the flexible electronic devices. Like Samsung introduced a new graphene-based batteries. Now they are also focused for mixing materials. And on the other side of environmental obligation, it is focused mainly on water treatment, like absorption of toxic ions and separation of toxic chemicals using membrane technology, and the extraction of palladium group metals, especially. As you know that yesterday, Dr. Rajiv Gandhi have already explained about how the PGM material was, the palladium group metal was extracted using the calix-serine materials. We are also focused, myself also focused on the extraction of palladium group metals using Maxine-based material with the substituent of sulfur materials for the functionalization. Then also we have focused on photodegradation studies of toxic molecules and also capacitive deionization also. So in the form of composite materials, it highly conductive and the high strength and low permeability polymers, and it has high toughness ceramic-based metal composites. For the energy application, I would like to focus on energy of first. So capacitors are nothing but it store and release energy by reversible adsorption desorption mechanism of ions at the interface between the electrode materials and the electrolytes. Until now, there are a lot of 2D materials was focused for the supercapacitor application, especially for molybdenum disulfide, vanadium disulfide, LDH, sulfur-doped LDH materials, and the metal organic frameworks and graphene-based materials, carbon nitrides, and recently added Maxine materials. This among the materials, Maxine materials showed exhibited a higher lower conduct resistance, higher capacitance, and a better and also showed excellent cyclic stability with 100% capacitance retention even after 1000 cycles of at the scanner 50 millivolt per second. Then initially group of people from China have developed supercapacitor application using Maxine-based materials. They intentionally developed porous materials and the Maxine porous and the material Maxine phase. They found that it is the best one. They showed the specific capacitance is more than 355 farad per gram with a scan rate of 10 millivolt per second with the help of 3 molar sulfuric acid as a electrolyte solution. The mechanism mainly follows for pseudocapacitance. If we use the neutral electrolyte, then it will form the EDCL mechanism also, which was also then the graphene-based materials. A group of people from China, they developed a graphene material which was compared with the Maxine materials also. They initially they took the graphene sheet and heated with different temperature from 200 to 900. They found that up to 200 degrees Celsius, they achieved more specific capacitance with the help of 3 molar KOH electrolyte. But when compared to the mixing materials, it's found to be lesser. And this is the simplest example I'm telling here. And also the mixing based material with the PVA, which showed the higher volumetric capacitance, which is 2 times higher volumetric capacitance than the graphene based material with the help of 1 molar potassium hydroxide as electrolyte. From the report of science, we have the titanium based mixing paper demonstrated excellent cyclability and the ability to store 300 to 400 Faraday per gram with a translated 3 to 4 times much higher energy than the commercial activated carbon as well as graphene based materials developed for capacitor applications. Not only in the capacitor application, and I would like to explain a simple method to incorporate some nanoparticle onto the mixing. Recently, there is a group from India who is working in South Korea who developed a manganese oxide nanoviscous and mixing material. The appropriate amount of mixing was added with manganese sulfate solution. Then the manganese sulfate solution was oxidized with the potassium permanganate. Then most of the manganese oxide was coated, intercalated into the basal plane of the mixing, which was confirmed by XRD as well as TEM image. The TEM image, you can see the carbon, manganese, and oxygen are similar patterns, or showed the similar patterns than the titanium, which means that manganese does not form any. The manganese does not form any bonds with the titanium. Instead, it forms with cation pi interaction with carbon materials. Also, it has shown the specific capacitance of more than 200 Faraday per gram, which is 3 times higher than the pristine forms of mixing, which also showed the more than 88% of cycling stability of even after 10,000 cycles. Also, this material is also compared with the graphene based material, the manganese oxide with the graphene based material. Then it showed lesser specific capacitance than the mixing based material. So we are also starting some works on supercapacitor application after joining to the Alapa University. The mixing material was given by my Professor Park from Kunpuk National University, South Korea. We have also started with some bimetal oxide and selenium doped and mixing. We showed the specific capacitance of 600, almost 700 Faraday per gram with 1 molar KO solution. See, we are at the starting stage, so we are also waiting for some spectrophotometric evidences as well as spectrochemical evidences to publish this paper also. Then not only in the supercapacitor application, there are also focused a few groups in South Korea have also focused on sensor applications, where they have taken titanium backbone of mixing for volatile organic compound gas sensing. Initially, the highly electron donor moiety of acetone, ethanol, methanol, and ammonia have taken for this study. They have observed on the mixing moiety. The mixing moiety has the functional groups of hydroxide and oxide on the edges as well as basal planes of mixing, which tend to form hydrogen bonding. And among these, ammonia has higher sensing responses due to large absorption energy, which was confirmed by TFT studies also. Then the absorption energy of ammonia is stronger than the other molecules, such as methane, carbon monoxide, carbon dioxide, and nitrogen dioxides at room temperature. Besides, there are a lot of applications are focused for lithium-ion batteries, fuel cell application, and proton up conversion reactions using mixing-based materials. I have not shown. I have limited time, so I have shown only the 2 applications of energy. Then I would like to move on to environmental applications. Since the hydrophilic surface is more beneficial for always the absorption of polar ions and the ionic species, any ionic species, the most of the termination of mixing has hydroxide oxygen functionality, which will helpful for absorption of toxic ions as well as complex with the toxic cations also. Initially, the Uric Ogasky group, with the help of Ogasky group, they have started with the introduction of sodium ions into the basal plane of this mixing. Then it forms a sodium form of alkylation form of mexin for utilized for lead ion removal. They confirmed that the sodium ion was intercalate rather than the formation of upper layer. This surface adsorption, it was intercalated between the layers, was confirmed by PXRD studies. You can see here there is a piston form of max space. Then the D space of 002 has been shifted towards the lower angle of 2 theta, which confirms that the structure has delaminated, which means that sodium ion has incorporated between the layers. Sodium ion has incorporated between the layers, so the sheets are get exfoliated. Also, further, with the help of hydrogen fluoride, then this material was adsorbed for lead ion with the initial concentration of 20 ppm. With the initial concentration of, I didn't show that, the initial concentration of 50 ppm. Then it showed that the adsorption was cation exchange mechanism as well as complexation. Then the material was again regenerated using the suitable eluent like nitric acid. Then you will get the original form of mexin. Then we can get again with the sodium to incorporate sodium. Then you will get the original form. Then we can utilize further. When we found that the adsorption capacity was much higher, that means 140 milligram per gram using this sodium form of mexin, then which was compared with some graphene based materials, then it shows lesser amount like 36 milligram per gram with graphene based materials, which is almost 4 times lower adsorption capacity of graphene oxide than the mexin based materials. This is the quite advantages of mexin based material. Then also one of my friends in Queen Phuc National University have started work on molybdenum disulfide with mexin nanocomposite to absorb mercury ions from the solution. He started with this is the simplest form of 2D interaction. There's some metal sulfides. The molybdenum sulfide has a 2D structure, and the mexin has also 2D. And the 2D interaction was happened. Then the sheets are arranged in a sandwich-like structures. The mexin molecule are just conjugated for several levels. Then you will get slightly delaminated structure, which was utilized for, which was applied for the development of molybdenum sulfide on the surface of mexin by a hydrothermal method. Then we confirmed that the molybdenum sulfide was intercalated between the layers rather than the deposition of the mexin phase by XRD results. Then the mechanism was explained well using the mercury was adsorbed on the mexin phase through electrostatic interaction, ligand exchange, complexation, as well as soft acid soft base interaction. Where since this molybdenum sulfide has a sulfur moiety which has soft acid, then the soft base of mercury will interact easily. Then the soft acid soft base interaction has happened with the help of HSAP principle. Then we can see the some images. We can see you can see the crystalline form of mexin. Then after coating with the molybdenum sulfide, the molybdenum sulfide has both the layers above and as well as the basal plane, the interlayer surface. I have also started some work on copper adsorption. We have also started some copper adsorption studies with the help of mexin materials, which showed the higher adsorption capacity. Initially we have started with the sulfur doped graphene material towards the copper adsorption, since sulfur is a soft moiety which can easily absorb by copper by as well as we know the well-known HSAP principle. The sulfur doped graphene material has shown lowest adsorption capacity compared with the other forms. When compared with sulfur doped graphene oxide, mexin showed little, almost 0.8 times higher than that of sulfur doped graphene oxide. Then we have optimized the concentration from sulfur doped graphene oxide from 5 to 50%. Then we get the almost 2 times, almost 2.5 times higher adsorption capacity than the raw forms. Then we have taken initial amount of 10 milligram per liter with a pH of 4.8. We have also checked the mechanism. Then the mechanism was complexation, electrostatic interaction, ligand exchange mechanism. We are also waiting for some more evidences to explore the particular mechanism. and it to be published. Then this was the first study using the mixin-based materials, and of course this paper will be soon published. This we have started with arsenic, since these ions like hydroxide and oxide on the surface of a mixin material will be more helpful for absorption of arsenite and arsenate. We have started with different lanthanum and zirconium forms of composite forms of mixing. We have purchased commercially lanthanum hydroxide and zirconium oxide, which was intercalated on the mixing phase. Then it showed lesser absorption capacity compared with other forms. Then also the another form of lanthanum zirconium, which was synthesized by simple one-step one-part method on mixing moiety, which showed the higher absorption capacity than the commercial phase. Also, we have developed already the lanthanum fumaric MOF moiety. From the MOF, we have developed lanthanum oxides, that means LOXX. Then we combined with zirconia moiety, then we intercalated on the mixing phase. Then we showed higher efficiency than the reported material for lanthanum based materials until now. Also, the interesting phenomena was that the lanthanum zirconia based material was showed almost 80 milligram per gram of absorption capacity than the arsenate phase due to the pH of the solution, where the arsenate has the pH is 6.2, which is highly the arsenic was in the +5 oxidation state, whereas the oxidation state of arsenite is 3 at pH 8.7. Until now, there was 0 oxidation state, so hence the arsenite is more highly toxic than the arsenite species. Then we found that arsenic by the metal ratio, which was 2, we confirmed that each metal can absorb 2 arsenic ions. That means each ion, lanthanum can absorb 1 arsenic, as well as zirconium can also absorb, as well as both lanthanum, oxygen, zirconia can form bond, lanthanum, oxygen, zirconia, which can absorb arsenic by bidentate complex rather than the monodentate complex. This is the most the valuable one for the absorption studies. Then the mechanism was complexation, electrostatic interaction, and as well as the Lehigh exchange. Then, when I was in South Korea, one of my juniors, Vigneshwaran, came to South Korea for his internship program. Then we have started some bimetal sulfides. There are also 2D materials which was intercalated on the mixing material for bisphenol degradation, where we have successfully attempted and we have successfully got results for the intercalation of mixing materials into the mixing materials. We have synthesized nickel, magnesium, layered double hydroxide, which was further treated with some sulfur moiety to get sulfur form of mixate, which this is the more beneficial. Sulfur is more beneficial to degrade another material due to the electronegativity also. Then this material was combined with the help of some surfactant. Then we found that this material is highly effective to degrade the bisphenol A. This was confirmed by the ESR results. Then this paper was accepted. This is the main mechanism behind how the bisphenol A also degraded. We have also tried to degrade and rhodamine B as well as phenol degradation. Both are working well on mixin based material, rather which was compared with the graphene based material, but it is higher efficiency and the lower rate of absorption capacity, lower rate than the other 2D materials also. Then another similar work was done here in Alhambra University. We have started the copper lanthanum sulfide and mixin for bisphenol A degradation. We found that these particular bimetal oxides are intercalated, confirmed by PXRD studies, when the space value was increased drastically from the 9.9 to 14.2. This material, the mixing material was totally delaminated. Then we found that good results using sonocatalytic degradation. Sonocatalytic degradation is nothing but sonication along with visible light. Then we have also checked the photo degradation, sonocatalytic degradation, photolysis with photocatalyst and sonolysis. Among them, sonocatalytic degradation was much higher efficiency than the other methods developed here. We are also looking for the better results on the mechanism part, and we found that it was quite impressive results we got. Then recently, there was one group from India who's working in abroad. They have also tested towards the carbon dioxide reduction using mixing-based material. This they developed some metal oxide, bimetal oxide on the mixing phase. They successfully incorporated to delaminate the mixing sheet to get the nano sheets. They have tested with for towards the carbon dioxide reduction. It found from the cyclic voltammetry, it found that they got the current density of 18.745, which is much higher than the other materials developed for this study. Then they have utilized carbon saturated solution in 0.5 molar sodium hydroxides. Besides, there are a lot of approaches like environmental approaches like membranes and desalination applications, as well as capacitive deionization was also approached, and they found that mixing materials will be more popular in forthcoming years. And to conclude, these super properties of mixing seeds makes them promising candidate than the other alternative materials like which will be the alternate material to the graphene and other 2D materials. Compared to the intensive studies on graphene, the investigation of mixins are still in embryonic stage. We are also working on the embryonic stage of supercapacitors as well as for the towards the water treatment studies. Also, when we applied bucket treatment, it's effective way to eliminate the surface functional groups of mixins, and we can also tune by the trial treatment to get the more functionalities. As well as we can also functionalize some functional groups through the chemical bonding as well as van der Waals interaction to effective utilization of energy as well as environment. Then I would like to thank my supervisor who built me what I am now, Professor Meenakshi, and the other staff members. Of course, they played a key role. They are all my teachers and the other who developed me, and the organizers of this webinar particularly. I would like to thank them. Then I would like to thank Professor Lee, Yonsei University, Professor Sasaki, my JSP's mentor, Kyushu University, as well as Dr. Park from KNU. Then I would like to thank the Pardimal Kalayan, Department of Industrial Chemistry, Alapa University, Karaikudi, as well as other department faculties in Alapa University. And the funding agency, I would like to thank, especially thank the funding agency like RUSA, JSP, NRF, KRF, UGC, as well as DST, and my co-workers and my master students here. And thank you for your kind attention, and stay safe and save life. If you have any question, kindly let me know. I will be happy to answer you, and as well as you can also type your question in the chat box. Then I will with your email ID so that I can answer you by email.
Thank you, Muthu Prabhu.
Thank you, sir.
Gautam?
Yes, sir.
So we have time for 2 or 3 questions, and then
Okay.
we will wind up.
Sure, sir.
Anybody want to ask question? Please raise your hands.
Or put it in the chat box.
Yes, Dr. Ruchi Dubey. Dr. Ruchi Dubey.
Hello, good afternoon. Good afternoon.
Yes.
This is Dr. I want to ask Professor Muthu Prabhu, is it possible to use these devices as a reusable devices? Maxine.
Sir, I couldn't hear voice. I couldn't get your voice.
Please repeat again.
Can Maxine be used as reusable devices? Like we are absorbing something on it, then afterward, by the desorption, can it be removed, some harmful substances from it?
Gautam, can you help me?
Can the Maxine is the reusable device for adsorption studies?
Yeah, of course. We are also using for arsenic studies. We have utilized the arsenic removal.
Can you use it again and again?
Yeah, of course. We can use it again and again, so many times. Since when we compared with graphene oxide after prolonged using of graphene oxide, then get aggregation.
How will you regenerate?
Say using sulfuric acid or nitric acid, depending upon their pollutant.
You can regenerate.
It can be regenerated.
Okay.
The main advantage of this material is when you use graphene, actually it get aggregated after prolonged using for regeneration study. But in the case of mixin, it has already the titanium in the phase, so it will not get easily it will not get easily accumulate.
Okay.
Won't it add to the metal toxicity?
So metal toxicity is aluminum. So if you using max piece directly, then aluminum will be leached out when you use HF. Then, but the toxicity is quite less compared to other LDH materials and MOF materials.
Good, sir.
Okay. Maybe we have one more question.
Of course.
Manimaran, Dr. Manimaran. Manimaran.
Manimaran is not there. Huh?
Yes. Saranya Sri.
Okay. Saranya Sri.
Saranya Sri from GRI Hyderabad.
Please go ahead, Madam. Saranya Sri.
Okay, sir.
Okay, Gautam, we will wind up. Okay. Concluding remarks by Professor MGS.
It's a duty to thank every one of you for participating in this international webinar. First, I should thank the Vice Chancellor in charge, Professor Sundaravadi, for giving the go-ahead signal. And I should thank the registrar for permitting us to go ahead with this webinar. It is my pleasant duty to thank my head of the department, Professor Anita Payas, and all my colleagues, Dr. Meenakshi, Dr. Yelango, then Dr. Ramesh, Dr. Satish Kumar, Dr. Kalimuthu, Dr. Srinivas Purmal, Dr. Arunachalam, Dr. Vijay Vadana, then Dr. Sivaraman, everybody. Of course, my partner in this webinar organization is Professor Abraham John, and he stood by my side, and in fact, he left no stone unturned for making it very successful. And for all his efforts, I salute you, sir, and I thank all my colleagues, the authorities of GRI, and Dr. Gautam, who was really toiling for over 3 to 4 days. And I thank all the speakers, Dr. Balakumar, Dr. Rajiv Gandhi, Dr. Kalimuthu, Dr. Gautam, Dr. Karthik, and Dr. Muthu Prabhu for their wonderful presentations. Though there were some issues regarding connectivity and all that, but they tried their level best, cooperated with us, and came out to the best possible things. So I'm indeed thankful to each one of them, and I'm thankful to everybody for making it a good success and getting about 500 nearly participants, and with YouTube participants probably it may run into thousands, but still we could have reach only through this Skype. So the technology inventors also should be thanked for this enabling mechanism they have devised, so which has enabled GRI to reach out to so many. And I'm very happy to say that this department always with the NMR facility, with SEM facility, and with LCMS facility helps everybody. And whoever wants to avail these, there are the informations are posted in the Gandhigram Institute website. So probably we'll be able to help you also. And I think it is certain that Gandhigram will become the destination for serious researchers, as you are able to see 6 scholars who have come out of the portals of these institutions doing very well. And there are many more. Probably if we have to organize webinars on by our postdoc students and others, we may have to organize several such webinars, because the list of students who have completed their PhD and who are settled in abroad, who are working in various universities as postdocs and faculty members, the list is long. So to that extent, this university has groomed the scholars, and I think we should we should congratulate the efforts of everybody for making it this webinar a successful one. So I thank you all. I thank once again Professor John. So one final word from John before we conclude. So over to Professor John. John, sir. Hello. Professor John, are you there?
Sir is not in online, sir.
Not in online, huh?
Yes, sir.
Anyway, so I thank Dr. Gautam once again. So thank you, everybody.
Sir is online, sir.
Online, huh? Okay. If he's there, call him. Okay. One final word from John, sir.
So once again, I thank Professor Seduraman for his concluding remarks, and also I thank all the participants for the patient listening. Of course, as he said, we have some technical issues. We hope that will be rectified in next our forthcoming webinars. We are also planning for next webinar. We will be announcing soon. And those who need that e-certificate, they have to submit their feedback forms. I think Gautam, today itself,
Yes, sir.
Yeah.
They have to complete their, yes. Today you have to, and please patiently wait for 10 days because we have so many participants. We have to prepare it. We will send to everybody. I am very sure that we will send each one of you, but please be patiently wait for 10 days. We'll send it after 10 days. Okay. Thank you. Thank you very much. See you once again.
Thank you.
In
Thank
another
you.
webinar. Thank you.
Thank you, sir.
Thank you, sir. Thank you.
Thank you for the opportunity.
Okay. Bye. Bye.
Bye.
Okay. Thank you.